Okay. We're back. 528. So we were reading on floating point literals, and that's what we're gonna do. Let me get my trusty. You know what? I should do something. Move this down to here. Move a little bit to the side for now. In fact, I might even do this just so I can have more clues here. Okay, so let's get back to this. All right, so floating point literals. Floating point numbers represent decimal values with a fractional component. They can be expressed in either standard or scientific notation. Standard notation consists of a whole number component, of a whole number component. Right, wrong. Oh my god. Followed by a decimal point, followed by a fractional component. Okay. So for example, 2.0, comma, 3.14, that's pi, comma, and 0.667 represent valid standard notation floating point numbers. Scientific notation uses a standard notation, floating point number plus a suffix that specifies a power of 10 by which the number is to be multiplied. The exponent is indicated by an E or E, capital E or lowercase e, followed by a decimal number, which can be positive or negative. Examples include 6.022 E23 or let me lower it a little bit. Okay. Or pi e exponent -5 and 2 exponent to the power of 100. Oh, that's pretty cool. Wow, this is pretty good. Floating point literals in Java default to double precision. To justify a float literal, you must append an f or f to the constant. You can also explicitly specify a double literal by appending d or capital D or lowercase d. Doing so is, of course, redundant. The default double type consumes 64 bit of storage, while the smaller float type requires only 32 bits. It's pretty cool. Hexadecimal floating point literals are also supported. Oh wow. But they are rarely used. They must be in a form similar to scientific notation, but a P or capital P or lowercase p rather than an E is used. For example, 0x12.2 P2 is a valid floating point literal. The value following the P, called the binary exponent, indicates the power of 2 by which the number is multiplied. Therefore, 0x12.2 power, the binary exponent of 2 represents 72.5. Wow, this is pretty good stuff, man. I didn't this wasn't taught for me in the course, but that's probably because this stuff is like really rarely used, unless in non-standard software development, and that's probably why that's there. Very likely that that's the case. All right, let me do something here. Okay, let's get back to this. All right, so now, chapter 3, we're still there. you can embed one or more underscores in a floating point literal. This feature works the same as it does for integer literals, which were just described. Which were just described. Its purpose is to make it easier to read large floating point literals. Works the same as it does for integer literals. Okay. When the literal is compiled, the underscores are discarded. For example, given double num equals 9 underscore 423 underscore 497 underscore 462 dot 0 semicolon, the value given to num will be 9 billion 423 million 497,862 dot 0. Okay, the underscores will be ignored. Oh, very good. I'm using the arrow now to make it a little faster so I don't have to move the mouse. Okay. As is the case with integer literals, underscores can only be used as separate digits. They cannot come at the beginning or at the end of a literal. It is, however, permissible for more than one underscore to be used between two digits, as it was the case with the other one. It is also permissible for more than one underscore to be used between two digits. Okay, it is also permissible to use underscores in the fractional portion of the number, or after the dot. Very nice. Double num equals 9 underscore 423 underscore 497 dot 1 underscore 0 underscore 9. Oh, that is so cool. It's legal. In this case, the fractional part is dot 109. Oh my god, that is so nice. I feel like I'm now getting to know Java like intimately, you know? After coding so many programs, this stuff I didn't know, like that you can use this hexadecimals as binary, decimals as binary. Wow, this stuff is pretty good. Boolean literals. Boolean literals are simple. There are only two logical values that a Boolean value can have: true and false. The values of true and false do not convert into any numerical representation. The true literal in Java does not equal 1, nor does the false literal equal 0. In Java, the Boolean literals can only be assigned to variables declared as Boolean or used in expressions with Boolean operators. Okay. Character literals. Characters in Java are indices into the Unicode character set. They are 16-bit values that can be converted into integers and manipulated with the integer operator, such as the addition and subtraction operators. A literal character is represented inside a pair of single quotes. All of the visible ASCII characters can be directly entered inside the quotes, such as A, Z, the at sign. Let's scroll up a little bit. Okay. For characters that are impossible to enter directly, there are several escape sequences that allow you to enter the characters you need, such as \tick. If you notice, there's like a little double thing there, and that's because, hold on, let's see if I can do this. I'm going to show you something. Okay. If you do this, yeah, this thing also is supposed to have a magnifying thing, but if you do this, if you check right here, there is actually but I don't know how to bring it up actually with this. I have to change this. Okay, so let's yeah, should be able to see it. So okay. So now let's disappear this markup stuff and let's get back to this. Okay. Okay, for the single quote character itself and uh, backslash n for the new line character. There's also a mechanism for that stuff that I knew. There's also a mechanism for directly entering the value of a character in octal or hexadecimal. For octal notation, use the backslash followed by the 3-digit number. For example, backslash 141 is the letter A. For hexadecimal, you enter a backlash U. So LU, then exactly 4 hexadecimal digits. For example, LU0061 is the ISO Latin 1A because the top byte is 0. LUA 432 is a Japanese katakana character. Oh, nice. Table 3.1 shows the character sequences. Let's look at the table. That's probably like much lower because that was not in the previous pages. All right, let's read. We'll get to the table. String literals in Java are specified like they are in most other languages by enclosing a sequence of characters between a pair of double quotes. Examples of string literals are hello world and double quotes, two back escape sequence and lines, double quote closing, and double quote escape sequence, double quote, this is in quotes, sequence, double quotes. Basically, with escape, oh, I don't know what Siri's talking about. Siri, shut up. Okay. Make me use my mouse. Okay, let's go back. Okay, so here, the double quotes that you see there, what that does is it allows for the quotes to actually show up when you print, because when you print the string within the double quotes do not print. But if you do it with a escape sequence or the backlash, and then you put a double quote on top of it following the backslash or the escape sequence, then that means that you want the double quote to show up. Okay, but it needs to be within the double quotes that contain the string and any of the character. All right, so I think we got to the table. All right, so escape sequence, description, octal character. Okay, but I thought we read that you only needed was it really? Octal character DDD. Hold on a second. I thought we just read. Okay. Use a backslash followed by a 3-digit number. Oh, yeah, you don't have to put anything, it's just a 3-digit number. So technically, the DDD is a 3-digit number, so it will give you an octal. That's what the table is showing. Got confused by looking at the 3-letter D's. But those letter D's are being read as chars, which in turn, being 3 have numerical value, which in turn, being 3 of them, represents an octal value or octal character. Isn't that interesting? That's how you read it. Okay, hexadecimal, you gotta put LU followed by 4 numbers. That's a single quote, double quote, backlash, carriage return, in new line, also known as line feed. Okay, form feed, a tab, a backspace. That's pretty cool. Okay, and space, I about the GDK15. Oh, that's pretty cool. I knew the space, but the form feed I don't know. And end of line, continue line applies only to text blocks. Oh, that's pretty interesting. I gotta see that in action to actually to really understand what that means. Okay, so that's the table 3.1. So let's keep reading. The escape sequences and octal hexadecimal notations that were defined for character literals work the same way inside of string literals. One important thing to note about Java string literals is that they must begin and end on the same line, even if the line wraps. For string literals, there is no line continuation escape sequence as there is in some other languages. It is useful to point out that the beginning of JDK15 had a feature called a text block, which gives you more control and flexibility when multiple lines of text are needed. Oh, I didn't even know that. At least I don't remember what they're talking. Oh, it's probably the... No, that's not multi-line text. That's not it. This is something else. We'll get to that much later. Okay, as you may know, in some other languages, strings are implemented as arrays of characters. However, this is not the case in Java. Strings are actually object types. As you will see later in this book, because Java implements strings as objects, Java includes extensive string handling capabilities that are both powerful and easy to use. This is pretty good. Okay, variables. Alright, so let's just keep going and we'll get to variables. Great. Okay, so variables. Alright. The variable is the basic unit of storage in a Java program. A variable is defined by the combination of an identifier, a type, and an optional initializer. Wow. In addition, all variables have a scope, which defines their visibility and a lifetime. These elements are examined next. That's interesting. Defines their lifetime. Oh yeah, because of the scope, of course. I got it. That's pretty nice way to put it, though. Never thought about it that way. Okay, so declaring a variable. In Java, all variables must be declared before they can be used. The basic form of a variable declaration is shown here. Type, then the identifier, that is the name. The equals to enter value. Then the identifier, and then equals and enter value ad infinitum. Basically, if you want to identify many variables at the same time, this is how you do it. Here, type is one of Java's atomic types, or the name of a class or interface. Class and interface types are discussed later in part 1 of this book. The identifier is the name of the variable. You can initialize the variable by specifying an equal sign and a value. Keep in mind that the initialization expression must result in a value of the same or compatible type as that specified for the variable. To declare more than one variable of the specified type, use a comma-separated list, which is what the example was doing. Here are several examples of variable declarations of various types, and note that some include an initialization. Okay, so pretty cool. Oh, you know what? It's interesting that in the second one, int d equals 3, comma e, comma f equals 5. It's actually initializing 2 and declaring 3. Oh, there. It declares 3 ints and initializing d and f. Okay, so that's pretty nice, actually. Byte z on 2. Okay. Pi. Okay. And character x each variable x has a value x, which is a larger capital X. Identifiers I choose have nothing intrinsic in their name to indicate their type. But Java allows any properly formed identifier to have any declared type. Okay, and then there's dynamic initialization. So although the preceding examples have used only constant initializers, Java allows the variables to be initialized dynamically. Using any expression valid at the time the variable is declared. For example, here is a short program that computes the length of the hypotenuse of a right triangle given the length of its two opposing sides. Okay, so this is going to be another chance to write in the nano and make more mistakes. Oh boy, this is cool. Alright. Oh, the program is in the bottom. I know you cannot see it too well, but the program is down there. So what I am going to, let me hold on a second. No, let me do it like that. Write it here anyway. So what we're going to do, let's see, how do I do this? Okay, so let's just do it. Okay, nano, what's the name of this class? Dyn int. Init, dyn init. So dyn init. Okay, nano dyn init dot java. That's the name of the file, and that's how we gotta save it. Okay. On straight dynamic initialization class dyn init. Oh, I was supposed to use a capital there. I think I messed up, so I'll make sure to fix that on the name of the file. You can see it right there. Okay, and then okay, static void main string RGS, and then let's use another one. Okay, so double a 3.0 comma b equals 4.0 semicolon, some space, and one day I'm not gonna need to look at the keyboard. One day it's gonna be great. Okay, so C, comment C is dynamically initialized. That is double C math. I think I need to import a class here. Oh no, you can just use that one right from there. Math that square a times a plus b times what 8, oh my goodness, a plus a times a plus b times b, a times a plus b times b, and then close brackets, semicolon. Okay, let's see if he remembers. He doesn't remember. Okay. So system dot out dot print line hypotenuse is, and then we print C. Okay. So what he's saying is that C was not technically initialized, but the function math dot square root will deposit the value so that C is initialized at that moment. Technically, it's not yet, but a runtime is supposed to initialize once it gets the value of math dot square. That's the idea. Okay, so here we go. I think we can save this. Let me double check. Quick check. Then init. Okay. Public static void main. Okay, I think I wrote it right. And let me dot Java. There we go. So that's more like it. And now skull Java compile, then init dot Java. Okay, it compiled successfully. That means I made no mistake. Woo! Okay, and now Java. There we go. Hypotenuse is 5.0. There we go. Oh, that's beautiful. Isn't that beautiful? But man, I think I gotta start writing this code in TextMate only because I can see that's not easy to read. Okay, so we're going to do something here. Let's see if I can. Oh, it makes it a little easier to read. That's what we're gonna do. However, okay. I guess this is good enough. That's good enough. And then we can go back to this. Well, you know what? Let's just move it behind the camera a little. Oh, right there. That's much better. Okay. And it's about to stop the recording, so we will run. We will run the program in the next video. Okay. Whew.